Okay, there's a little bit of work done already on this question, but I'm not going to start it over. So I had a little problem with the camera a few moments ago. So let me begin again. But as I said, not completely from scratch. Let's just focus on the question here for the moment. So maybe I'll force you to do that. So this is the question that we're given. 2.5 moles of a perfect gas is basically the working substance of a Carnot engine. The Carnot engine undergoes the Carnot cycle, which cycles between two temperatures, a hot and a cold, and there are different ways that sort of machine is going to be described to you in a question, but you can usually determine that there are two temperatures, a hot and a cold. Shouldn't be more than two, and we know the initial volume, and we know the work of the first step. So in a cycle, sometimes you might think, well, if it's a cycle and completely restarts all the time, there really isn't a first, second, third, fourth step, but there is. The first step is always the the first step is always the isothermal expansion in a Carnot cycle. And so when it tells you that the work of the first step is equal to minus 16300 joules, or 16.3 negative kilojoules, that is the work of the isothermal expansion step, because that is the first step. And that first step is isothermal at the hot temperature, the higher temperature. It is followed by an adiabatic expansion. So we go expansion, expansion, followed by compression, compression, specifically isothermal compression, and then an adiabatic compression. So I want to take what we have here and actually put it into the table. There's a little more than what's given here because, as I said, I had started the problem already. What is actually highlighted in green are answers arrived at. Actually, all these are, so I'll just do this. There we are. So I think that comes through on the camera so you can see what was actually given. So 2.5 moles all the way across, state A, B, C, and D. The pressure I just found, I'll show you that in a second, but the volume was given at 12.0 liters. The T hot temperature, so T hot you should put in for your first two states. Here 535 Kelvin for each of state A and B, and the cold temperature is 125 Kelvin. So we put that in states C and D. So the moles go right across, and the temperatures I know. You may not always be given the same sort of given data at the beginning to start your table off, but this is one version. Sorry, I have a really squeaky chair in this one office. And the work was given. In fact, the work was given, not the Q. So I'm going to highlight this as green, and oops, this was actually given. So just point that out. So given the work of the first step, minus 16300 joules. So with this and your temperature and your volume and your number of moles, where do you start? Well, I can use PV and RT here when I only have one unknown, and the one unknown was pressure. So that's where I started. Okay? So we did PV is equal to nRT, and isolated for pressure is nRT over volume. We went through the calculations, and we got a 3 sig big answer, 9.15 atmospheres. And that's what's written up here as my first solution in green. Then we came down here and we said, all right, since it is isothermal and a perfect gas, those two bits of information lead to the conclusion that the internal energy change is 0, and therefore the sum of Q and W is 0, or Q is equal and opposite to work. And the W was given, so all I've done in the solution table is to change the sign to a positive for the heat. And so there's another one. Delta U is 0. Delta H is also 0 in this case because delta H is delta U plus the delta of the PV. PV is a constant for an isotherm, but if we didn't remember that and we replaced it with nRT, N and R and T are all constant. So, and if we still didn't catch on and we had replaced delta PV with an NR delta T, recognizing that N and R are constant and forgetting the temperature is, until we wrote it as delta T and realized, oh yeah, that's 0 too. So delta H is 0. And so delta U is 0, delta H is 0, and then, excuse me, we are left to fill in delta S. Now, it may not be the case that you're moving across linearly, filling these in one at a time. Sometimes you can jump forward and get one, and then by doing that, you're helping yourself fill the gap subsequently. So, yeah, I guess that's where we were. I'm just going to move that up here. Okay, so delta S. What is delta S for that first step? Yeah, it's usually a good idea to go back to the thermodynamic definition, first principle. And it's the Q reversible over temperature. Yeah, and we have the Q reversible. Okay, so of course delta S, and you don't have to do all of this out in detail, but again, this is a tutorial. So I integrate, and the reversible Q for an isothermal expansion, where delta U is 0, the reversible Q is the reversible work. And we can integrate that because we actually have a value for the work. So let's just take that right out. It is equal to the reversible work divided by temperature. And again, we have the values for this because we were given the work and we know the temperature. Let me back up a bit. I forgot about a sign. So if Q is equal to the negative W, then that should have been a negative here. This is a negative here. The value for work was given as minus 16300 joules, so the negative of that is the positive, and so it is simply 16300 joules over the temperature, which is 535 Kelvin, and that is 30.467. So 3 sig figs, 30.5. And that's where that number came from. Okay. So then I go back to my table and I update it, and I put 30.5 joule per Kelvin. Yeah, so that was already in the table because I had done this calculation. The camera was working. Excuse me. Over here, starting to yawn. Okay, let's bring that table back and decide what we do next. What can you do next? This is an isothermal expansion that links these. I need pressure, I need volume. If I had one, I would just do PV and RT to get the other, but we have the work. How about we use the formula for work to get us to the second volume? Work is minus nRT ln V final over V initial. And the only unknown there is V final. Minus nRT ln of V initial over V final equals work. So let's do that and rearrange. Good. Work is equal to a minus nRT ln V final over V initial. And so if I had my value for work and I divided it by minus nRT, that would equal the ln of V final over V initial, which is the same as the difference of lns, V final minus ln of V initial. And so I take my work, I put it over minus nRT, I'm going to bring over plus ln of V initial, and I'm left with ln of V final. So what is the value for my work? It is a negative 163.00 joules, and that's over a negative, so right away those are going to go. My moles, that was 2.50 mole, 0.08206 liter atmosphere per mole Kelvin, temperature 535. I'll add to that the ln of V initial 12.0. Now I'm not going to put liters here because you don't take the ln of a unit, you just take the ln of the number, so you drop those units. That tells you that what you're solving for, ln of V final. So all of the left hand side here should give me a number, which means that all the units here need to cancel. This is no units. This has no units, but I'm allowed to stick the units up when I do inverse ln of that answer. Stick the units of liters back on because those are the units that I dropped, essentially. Oh, so let's look here for a moment. So we have joules, and we did moles, we did liter atmosphere per mole Kelvin, but that's not going to cancel. And so really what I should be using here, instead of this term, I should be using 8.3145 joule per kmol. Now those will cancel, the moles and the Kelvin, whoops, with the Kelvin, and that's all great. Okay, so let's calculate this. So 16300 divided by 2.5 divided by 8.3145 divided by 535. So that whole term there is 1.465, and I'm going to add it plus bracket 12 ln close bracket equals 3.95. So my ln of V final is equal to 3.95, 06. The number is still in the calculator. So I need the inverse ln of that, and on my calculator that's, well, it's e to the x, but on my calculator it's second function. So V final is 51.969 to 3 sig figs, so I think that's 52.0 liters. Does that make sense? It's an expansion from 12. That's a lot of work. Yeah, sure. 52.0 liters. So let's bring that back and fill it in. 52.0 liters. And now I can use PV-nRT to find the pressure. Right? Let's just keep scrolling here. Again, PV equals nRT. Therefore, pressure and RT over volume. And in this case, 2.50 moles. Now I'll use the 0.08206 liter atmosphere mole Kelvin. Temperature. What is the temperature still? State B. Right, 535. And the volume, 1 over volume, 52.0 liters. Okay, moles, moles, Kelvin, Kelvin, liter, liter, I'm left with atmosphere. Punch in the numbers. 2.5 times 0.08206 times 535 divided by 52. 2.11. That's what I get. So this is P sub B. We're following along. 2.11 ATM. And does that make sense? Isothermal expansion. Yeah, we get a pressure drop. 2.11 ATM. Good. Takes a long time to do these filling this table. Okay, that's good. So now what? Now we have an adiabatic expansion. Let's pull this back here. Adiabatic expansion. I do know my delta T. That's usually the big thing to find, isn't it? Once I have delta T, I can do a lot. But hey, since we know it's adiabatic, what can we fill in right away? What can we fill in right away? Yeah, adiabatic means that there's no Q. And so this is 0. And there's no Q, there's no reversible Q, so delta S. So 0. These guys are going to be the same, work and delta U. They're the same. So I'll do that. And they are equal to NCV delta T. Let's calculate that. Work equal to delta U. And that is NCV molar delta T. I have 2.50 moles. What value will I use for the CV molar? I don't know what gas it is, but it's a perfect gas. Right, so CV is 3/2 R, CP is 5/2 R. So 3/2 R, and the R is 8.3145 joule per K mole. And now my delta T, it's cooling, it's an adiabatic expansion, it's going down to 125, it started from 535 Kelvin. Moles, moles, Kelvin, Kelvin, and my answer will be in joules. Okay, so 125 minus 535 times 8.3145 times 3 divided by 2 times 2.5. And I have 12783. And it's negative 12783 joules. So in 3 sig figs, 12800, or we like to use kilojoules, 12.8. That's up to you, your unit. It's a negative, yeah? Does that make, yeah, it's expansion, so it should be a negative. 12800. Lovely. Okay, let's do delta H right away. Get that out of the way. Delta H equal to delta U plus delta of the PV, delta of the nRT, I can make that change. nR constant leaves me delta T. Delta U I just found out. And I'm adding to that 2.50 moles, 8.3145 joule per kmol, and my delta T, 125 minus 535 Kelvin. Here we go. 125 minus 535 times 8.3145 times 2.5. So that part is minus 8522. Let's get this in view. Just so you can check your numbers. Against mine. 8522 joules. So I'm adding 128. And that is 21,322. And let's trim it back to 3 sig figs. It's negative 21300 joules, or 21.3 kilojoules. Checking my answers because I did this out on the back of a sheet of paper already. Okay, and let's fill that in. Minus. So that is a delta H minus 21300. Super. And none of these were given, so these are all highlighted green, indicating that they are answers. Good. Adiabatic. How do we find a V final in an adiabatic, and how do we find P final in an adiabatic? Well, okay, good question. We could, short answer is we'll find one or the other using an adiabatic formula, but then we'll find the remaining one just simply using PV and RT on the state, right? Right? So I can use my formula V final equals V initial times whatever that temperature ratio is in the exponent that has heat capacity in it. Once I get that, I'll use PV and RT to get pressure, or I use, if I can, the PV gamma is a constant, isolate for P final, find it, and then use PV and RT to get volume. So let me just check if I know it's, see what in fact I did. U00. That's a U. Step C for the isothermal motion. I'm just looking for my formula. Looks like I did it a different way. Alright, let's do the V final one. I'm not going to derive the formula because we've done that elsewhere. We know that V final is equal to V initial times T initial over T final CV R. Yeah. And yeah, you know how to derive that one, so let's just use the formula for this question. Okay, so do I know everything to put in here? I think so. V final equals V initial, so I'll just flip this back. So my V final is here, my V initial is 52. So you can just think of that engine going from 12 liters up to 52, and now another expansion, and then compress. 52 liters. Now the T initial, just bring this back here for a second, because we are looking for this guy, and it's linked, so this is my initial and this is my final through the adiabat. So my T initial is 535 and my T final is 125. CV over R. CV, 3/2 R over R is is just 3/2, of course. We've done a lot with the T final equals T initial with the volume ratio. So they look so similar. They are very similar. And that exponent ends up being 2/3, but this one is 3/2, or 1.5. So let's do the calculation and get V final. So what is that? 535 on 125 is 4.28. And then I want to use my x to the y on 3/2, but 3/2 is 1.5. So it is 8.85 times 52.0. Is this a compression or an expansion? Yeah, it is an expansion, so that's fine. So it's 52.0 liters times 8.85. So let's keep going with the calculation. Yeah, oh, it expands all right. 460. Sorry for the pause, I was just making sure it made sense. It's 460.43. I'm just going to do this to give myself 3 sig figs. And that's my V final. So I can put this up here. What did I say it was? 460. Now let's do PV and RT to get the pressure. .08206 liter atmosphere per mole Kelvin. The temperature is 125 Kelvin, and the volume we just found is 460 liters. So we have, that's still there, so I could take the reciprocal, but I can't see it in the calculator. Squared. 2.5 times 0.48206 times 125 divided by 460. 0.0557. Is that what you got? For the pressure. Yeah. Right here, 557. Awesome. So we found that, and we found that. Okay, let's have a look here. I feel like we're going I'm going very slowly. Now, this is isothermal compression from C to D, isothermal compression. So I know that my delta U will be 0 and my delta H will be 0. My Q and W will be equal and opposite, and the delta S will simply be the work divided by temperature. And again, I can use my, well, no, I don't have the work. Hold on. Now what? How do we get that? I'm going to let you think about it. And time's getting long. I don't want the video to get too huge, so I'm just going to cut it here and we'll come back and complete that side of things.